of the most important events in terms of the safety of nuclear energy, and that was obviously the Fukushima plant. There is nothing that compared with it. It happened also somehow in our lifetime. So in that case, our topic today is the Fukushima accident. And we would like to, as we go along also the same way as other main accidents, identify the equipment failures, the human errors, as well as the design faults or design defects. Along this line, we also identify the unique features of the Fukushima accident, in that it also was caused by a natural event, the tsunami. But nevertheless, it was not well designed to withstand the effect of the tsunami, as we'll see as we go along. Japan is a country that doesn't have enough fossil fuels like other countries like the United States or Russia or some of the European countries except France. So it has been generating about 30% of its electricity from nuclear power plants. And they are well designed in terms of withstanding earthquakes and even tsunamis. Earthquakes and tsunamis in Japan are very common. It is an area that is seismically active. So their power plants are subject to events of earthquakes in general. I said that they had quite a few nuclear power plants, 54 of them. The United States have about 96, so they are half of what the United States have. And these 54 nuclear power plants were positioned at 17 plant sites, both on the west coast as well as the east coast of Japan. So you could see here, for instance, that one plant here, Suruga, has two units, but Kushiwazaki Kariwa is 7 units. And these were all on the west coast of Japan. They were not affected whatsoever by the earthquake. On the east coast of Japan, we find the 1, 2, 3, 4 units of Fukushima Daiini. I think Daiini stands for number 1, and the Fukushima Daiichi, that was 6, 1, 2, 3, 6 units. And in that case, at the 4 units out of 6, 1, 2, 3, 4, 5, 6 here, were affected by the earthquake and tsunami that happened at Fukushima. The tsunami waves propagates at quite a high speed. I was asked when I wrote that chapter, oh, wow, how much is the speed of propagation of the tsunami? I found that it is about 800 kilometers per hour, faster than an airplane, and it happened somewhere here in that case, the Pacific Ocean. However, the event was very important because it's very close to Tokyo. And luckily for Japan, the winds that blow in that area took the radiation out to the open sea, and it didn't carry out to the metropolitan area of Tokyo. Otherwise, they would have to vacate it, and would have had been a much more serious situation. So when the earthquake happened, Japan's Nuclear Industrial Safety Agency, it's named NISA, and proclaimed basically the event. Notice it's not September 11, 2001. It has an interesting date here. It happened on March 11, 2011. And the Fukushima Daiichi, I think Dai stands for the plant name, and Ichi is number 1. So that's plant number 1 site. And later on at the Fukushima Daiini, Ini here names number 2. So initially, the emergency situation happened at the 6 unit site here, Daiichi. and then later on at Daini. The reactors Daini were not affected. The reactor single unit as Tokai was not affected. It was 4 out of 6 units at the Fukushima Daiichi. One of those units here was totally shut down. It was not operating. Another unit had the core taken out for maintenance. So basically it was not also operating. In that case, 4 of the units really were subject, out of 6 subject to the accident that is very famous in that case. The reactors had all boiling water reactors designs. We'll see the design as we go along. And it was built by General Electric as well as Toshiba. Both of the companies have been building nuclear power plants. As we discussed earlier in the chapter on the safety effects of earthquakes, you'll find that they measured an earthquake on the magnitude scale. Remember, the Richter scale is a magnitude scale, or what appears on the seismograph. And the magnitude, the scale was 8.9 to 9 on the Richter scale. And the tsunami happened at the bottom of the ocean. And in that case, it generated waves that were 15 to 9 meters in height. That's quite a large kind of magnitude in terms of the earthquake. You'll find later that there was let's call it a shield built to prevent water from hurricanes to affect the plant, but it was not at the height of this 15 to 24 meter high wave. As we know, Japan is in what's called the Pacific Rim of Fire. Rim of Fire there because the tectonic plates are surrounded by volcanoes. The tectonic plates collide with each other at that point and are caused as a result very common earthquakes and very common volcanic eruptions in general. The Ring of Fire has about 100 active volcanoes and is subject to 1,500 earthquakes per year. Almost every day, 3 or 4 earthquakes happen in that. The coastline historically, or called Sanrico coastline, had 2 major earthquakes in the last 120 years. One of them in 1933 was of magnitude 8.4 on the Richter scale. So it was a very much less than the 8.9 to the 9 that was experienced by the Fukushima site in 2011. This one that was occurred in 1933 generate even much higher waves in terms of a tsunami from 15 to 24 meters. It generated a 92 feet high tsunami and it resulted in the deaths of 3,000 fatalities. Another major earthquake happened. It was a lower magnitude 7.2 in 1896. This one also produced a very large tsunami, 100 feet height, and that one resulted in 27,000 deaths and missing people. It's very interesting to find that the latest earthquake did not cause any deaths in the nuclear part of it, but in fact, there had something similar. About 28,000 people were killed by unfortunately, by the tsunami itself. They have historical records dating back to the year 1600. And this data that they had inspired basically the designers of the plant to suggest that the largest earthquake that they can think about is an 8.6 magnitude on the Richter scale, whereas, so they designed it accordingly. However, what was felt in this particular earthquake was 8.9 to 9 on the earthquake in general. Official records dating back to 600, of course, suggested the design, and it was not really, unluckily, the right number in general. There was an earthquake in the year 869 that produced also a tsunami. It reached 2.5 or 2.5 miles or 4 kilometers inland with wave 26 feet or 8 meter high. The tsunami wave that originated about 125 miles or 200 kilometers to the east impinged on the 6-meter protective wall. I'll show you that picture of the wall later on, and simply drowned the wall. It overcome the wall. That wall that was built was meant for protection against hurricanes, not against tsunami. Tsunami, by the way, as I know in Japanese, means harbor wave. So it has been affecting the fishermen as a profession in Japan. And when the tsunami wave comes into a constriction, the entrance to a harbor, you'll find that the energy concentrates itself and the height of the wave become very much higher, and they penetrate in that case, the harbor, and cause great destruction among the fishermen boats in that case. Here is actual pictures of the tsunami. You could see here boats along the shoreline, and the wave overcame any kind of roads here along the shoreline. Look here at the fishing boats being pushed from mooring there along the coast into the mainland itself across a road. And here you see too that it overcame even dwellings on the other side of that river here with bridges on top of it. And you could see that all those houses became fully underwater. And we cannot underestimate the force of the water in that case. As a result of the accident, according to NOAA in the United States, luckily the radioactivity was spread from the site of the accident there into the very wide Pacific Ocean. Some of it, in fact, reached the west coast here, as you could see here, if you follow it, the coast of the United States, not just North America, but even South America. But lucky for the great metropolitan areas around Tokyo not to be in the direct line. This would be where most of the radioactivity would have settled. And some of it, in fact, found its way around the Pacific Ocean into Australia in general. So it was very lucky event in that the great metropolitan area of Tokyo was not affected. Otherwise, the fatalities would be much larger. When tsunamis hit dwellings, you could see here that they compound the effect of destruction by the running water by causing fires here. You could see here that some fires have been caused in the Fukushima area, and you could see that the water came in from this direction, flooding homes, actually carrying them, destroying them in its path. So most of the destruction was from the tsunami itself. And this is a picture immediately after the tsunami. And you could see that it totally, absolutely, totally wiped up a whole town, Riko, Tenzataka. And they show the picture here after they basically removed the rubble and total devastation, total flattening of the landscape. This is a picture of that wall that I suggested was built to protect against, well, they suggested it's tsunami, but in fact, it was maybe more against hurricane waves. And you could see here 4 of the units. We said that we had 6 units at the Fukushima site. You could see here large towers. They'll have a role to play in the accident later on. Those towers basically were interconnected for the ventilation of the plant itself. One design flaw that we'll see as we go along is that the ventilation ducts were directed from one unit to another. And those ventilation ducts carried the hydrogen. So in one plant where there was no real damage occurring, the fact that the hydrogen was directed from another unit became what's called a common cause feature. So the 4 plants or 4 units should have been designed according to fault tree analysis and event tree analysis to be independent of each other. So in the same way as in the Brown's Ferry plant, the ducts containing the instrumentation and the control cables came in from the same duct. One accident caused an accident in another unit unnecessarily in that case. We'll have lots of documentation from TEPCO. TEPCO stands for the Tokyo Electric Power Company. And some of the documentation is true, but some of it is some kind of massaged to hide the responsibility of the Tokyo company. In a way, there were some design flaws. This is the siting of the plants. You could see here 1 plant, 2 plants, 3 plants, 4 plants. And this picture immediately shows us that shield against hurricane waves. And they really built the plant on an artificially flattened area, very close to the surface of the water. And I can show you pictures of plants also in Japan that were built much higher, so they were not at the same kind of risk as the Fukushima plants. So this picture shows us that it was very close to the level of the water. And these are pictures that show us really how the tsunami wave coming in from the ocean here immediately overcame very easily that basically the protective wall that was protecting the plant. The tsunami wave, as you could see here, simply overcame the whole thing. And here you find that that wall basically did not offer any protection whatsoever against the incoming tsunami wave. Interesting enough, you find the boat here. Boats are a good place to be in terms of safety, in terms of a tsunami, because all they can do is simply ride the incoming wave. The incoming wave comes in, the boat simply rises along above the wave and then settles down. Before the wave hits the area where it is hitting, you'll find that the water on the shore empties up. So it goes back to the ocean. And many people mistake that if you are on an island where a tsunami is happening and you see the water receding back into the ocean, that is a sign that a tsunami is coming on its way. Run for your life to any area that is high ground. Now look at here, these are fuel tanks behind the protection wall. And look what, when that wave from the tsunami overcame the wall, look at how the height of those tanks have been buried, and any vehicles that were stored in the area basically became totally floating or under covered with water. This again shows us the 2 units 5 and 6. The 2 units, as I said, there were 6 units there. 4 of them were affected by the accident. 5 of 6 were not affected. Why? They did not go and flatten the ground close to the seashore there to build the units. They were intentionally built on high ground by the General Electric and Ebasco companies, and were not affected whatsoever by the accident because they were designed and built on high ground. Not so. I make the point that it was a bad design to try to build the plants on flat ground that was flattened very close to the seashore, to the level of the waves, and not being provided with protection by that wall that was meant for hurricanes, not for tsunamis. So you find that the wave here overcame the defense that was thought to be protecting the plant, and a new type of accident, in fact, has been generated in that case. This is a diagram from the TEPCO company, Tokyo Electric Power Company, and it shows us here the level of the plant itself, and they suggest that basically the tsunami wave overcame the seawall. You see the seawall here by quite a bit here. Total overcame it totally. These are seawater that were bringing in pumps to cool the plant. It was cooled by sea water. and went even up higher than the ground level of the plant. So in that case, the water found its way into the plant itself from at the lower level on the floor, and flooded the basement of the plant. And there you find another design flaw in that the safety equipment was located in the basement of the plant where it got flooded by the water. So you find that this is really unit 1 to 4 were all at the level. This is the underground of the plant itself, and this is the building entrance. This is EDG. EDG is emergency diesel generator. So the emergency diesel generators were underwater. The power panels that control the electricity were underwater. A makeup water pump that would have provided cooling for the unit for the decay heat were also underwater, and the water simply flooded the basement of the plant. And this basically identified a new type of an accident that people now call the flooding accident. As a result of that accident, somehow on the Mississippi River, the United States had 2 nuclear power plants I'll describe to you before the end of the chapter. And because the Mississippi River flooded in June, they simply were able to shut down the plants as a way of protection from the information that came in from Fukushima. But later on, they decided, the utility decided that it didn't want to take the risk. So they basically shut down the 2 plants on the Mississippi River here in the United States. So EDG is the emergency diesel generators, or what we called earlier the emergency core cooling system, was underwater. And we know that electricity and water don't go together. So what happens in that case is that the plant now did lose all its safety equipment. And to compensate for it, nuclear power plants have also a connection to the grid. And if you have want to have fun, go on the Google Earth and follow the power lines coming to the plant from a transformer station 8 kilometers from the plant. And you notice that that plant, that switch yard that would provide power to the plant was damaged in the earthquake. All right, so now the plant did not have its own power. It lost its own power, and it lost also, like for all nuclear power plants, they must have at least 1 or sometimes 2 connections to the grid to get power to run, of course, the safety equipment, and to also provide a replacement power for the control systems. So the plant did not have power, and it did not have power from the grid, and this is designated as the station blackout constant. So the station became totally, literally black. I'll show you a picture of the control room that turned black. There were also some safety equipment like batteries, and those batteries, lo and behold, they were also positioned in the basement, and they also became flooded. Number 2 unit and the diesel generator is located in another building, such as the reactor buildings. This shows us basically the bottom of the turbine building where that safety equipment is positioned. There is no doubt, according to TEPCO, the utility, that the water basically went above the ground level, and that's about 14.5 meters. Unit 1 to 4, basically the flood height was 15 meters, and unit 5 and 6 was 14.5 meter high. Importantly, the emergency diesel generators that are there to cool the plant in the case of a loss of power were flooded and were not operational in that case. We studied before the concept of the earthquake magnitude and strength, so I'm not going to repeat this because we covered it separately in a chapter. But some information is very interesting here in that the energy release from the accident was about 480 from the earthquake, 480 and 80 megaton of high explosive TNT, which is trinitrotoluene. The largest ever nuclear weapon that was exploded was in the range of 65 megatons. That was the Tsar Bomba that the Russians exploded in Siberia. The Mount St. Helens volcanic eruption was only 10 megaton of energy. It tells you how much energy really was released from the earthquake itself. The seabed buckled along a 300-kilometer stretch, twice distance, well, or almost a distance from here to Chicago, an estimated 67 cubic kilometer. A kilometer is 1,000 meters of ocean more moved towards 860 kilometers of the Japanese coastline, with a wave that is estimated to have reached 24 meters in height. Now, as we said, the design of the largest historical earthquake was in the range of 8.4, but that earthquake, 8.6, sorry, that earthquake was magnitude 9 on the Richter scale. So the energy release there was beyond any kind of historical event that happened in the past. And I describe here that the energy release was much higher than expected, 32 times what is expected in the design calculation. So I'm not going to repeat this at all. Again, we identify the accident immediately as a station blackout accident, but later on now we also add to it that it is also a flooding accident. This is the simple way of showing the plant configuration. A boiling water reactor has the control rods coming in from the bottom. So in that case, you find that the pressure vessel has penetrations here from which, if the core melts down, it can melt the seals of those control rods and find its way below the reactor core, the reactor vessel. In that case, if it meets water, then we have a big problem. We have a situation of what we call a steam explosion. Another interesting aspect of the design as a boiling water reactor is that boiling water reactors, in the case of an accident, have what is called a core spray. So if you lose the coolant to the core, you find that that core spray starts spraying the core with water. Well, obviously, if the core has been uncovered, it will be very hot. And here in that case, you find that water now interacts with a very hot metal. And we have written that equation earlier, and that if you bring in water and you pass it on iron, this is a way to produce hydrogen by simply oxidizing the iron or burning the iron, if you want to call it. In the case of a nuclear power plant, here is the steam now at high very temperature interacting with zircaloy. Zirconium is chosen because it has a low corrosion or high corrosion resistance, as well as low absorption for neutrons. So, you end up generating hydrogen and zirconium oxide. Oxide is basically, when you say oxide, you say, you are burning it. When you have charcoal, carbon, and you oxidize it, you are burning it in that case. So this was a feature of the accident. We do not understand so far what was the contribution of the core spray, and because definitely hydrogen has been released in that accident. You have, of course, coolant recirculation pumps that would recirculate the coolant in the case of a loss of coolant. Now look here how the equipment have been drowned. This is from a video. I took some video grabs, screen grabs. This is tanks here, and this is the entrance to the basement of the plant. The water starts flooding the area, as you could see here. Look here at those tanks, how far they are flooded. They are flooded almost to their full height. There were vehicles here that was carried by the water. And then, of course, the water, after hitting the plant, retreated back to the ocean. However, You could see here the tanks here being, the water has left them, but look at those cars here that were flooded and carried out, hanging up around. Now, all the water that leaked to the basement had nowhere to go, so it stayed in the basement and affected the safety equipment. So that was the part in the emergency core cooling system that we spent some time figuring out in the case of the WASH 1400 type of report, basically it was a loss of coolant accident also in a way. For emergency at nuclear power plants to provide controls even if the power is lost, they have what they call coping batteries. They are still available, and they were provided to provide emergency cooling. These could deliver about 12 hours until external. It gives time, winning time. External or on-site power could be restored to the plant. At 2 hours from the earthquake, the TEPCO utility acknowledged the situation, and at 9 minutes later notified the responsible authorities in Tokyo. At 7 p.m., they declared the nuclear emergency, and that immediately prompted evacuation of the nearby population. And later on, they expanded the area of evacuating the population to 20 kilometers when they discovered that radioactivity has leaked, and within 24 hours, the population was vacated, and in that case, there was no any loss of life. Now, of course, you find yourself with the damaged control system, the damaged safety systems, and the operators of the plant had to deal with our decay heat removal system. And we studied that decay heat removal. Some people call it residual heat. Some people call it decay heat. Some people call it after heat. Some people call it after glow heat, but it is the same thing. And under normal conditions, that excess heat in the boiling water reactor is rejected by bleeding steam from the steam lines, and then it is quenched in the main condenser in the turbine part of the plant. A mode of the reactor heat removal system consists of 4 pumps, 2 heat exchangers, and their associated piping and valves. So this is really the containment structure. And in that case, you could see that the plant had 2 containments. One, a pressure vessel, as you could see here, then another containment called the dry well. If piping gets stuck, like in the 3 Mile Island, the steam is taken and basically bubbled out, or it's called quenched, in the pressure suppression pool that we know is in the form of a toroid. And that area here under the core is expected to be left dry. No water should be there. It's called the dry well. The control rods come in from this area. Apparently, that area flooded, and it created a suspicion that maybe the events of a steam explosion may have happened in general. All right, so let us look again at some detail about the safety equipment. It's very ironic that the safety equipment again was based in the basement. And one of the safety equipment basically had a turbine. That turbine was getting steam from the main steam line, and it would be rotating a pump. And that pump would get water from the condensate storage tank to provide a source of water for cooling the reactor core. It also would get water from the pressure suppression pool to cool the core in the case of a decay heat need for cooling. The interesting thing is that I'll show you later as we go along that that turbine and that pump were located, guess where? They were in the basement. So in that case, that safety part of the plant, the reactor cooling system, was not available for cooling the decay heat. So after it got flooded, the decay heat was not available, and the core spray was generating probably hydrogen in the system in general. The reactor had what's called the main steam isolation valves, MSIVs. These are very large valves. You could see the coils here, the steel coils. And these valves evacuate the containment structure in the case that there is a release of steam. The interesting thing is that later on they discovered that the pressure in the containment rose to such a height that those springs here or the pressure control of those steam isolation valves was not possible. So that was another design flaw that is described in the description. As a result, you'll find that the containment structures shown here and here started out filling up with steam, but not just steam. The core spray system caused hydrogen to be generated. And this is a picture from a helicopter. You could see here that the steam was leaking from the top of the building. It was not just leaking from the top of the building, it was also leaking from the vents or the towers to the atmosphere. As I suggested, those steam isolation valves were not able to be operated. Later on in the accident, the operators operated some hand kind of valves, but the steam, this shows here the light bulb, inverted light bulb design and the pressure suppression pool of a plant. It takes a containment atmosphere and tries to release it to the environment. Obviously, in that diagram with the helicopter, you could see that that was not the case. It was being released from the containment structure itself. Definitely, steam is showing here. Another flaw in the design, these are one unit and the second unit, is that those steam lines were containing now hydrogen were diverted in unit number 4 that was not in operation. And as a result, it was subjected to the hydrogen and it had also a fire, even though it was not operating. So the design of those units were not right. Here is a display from TEPCO that shows us the design pressure. And on March 15, remember the accident started on March 11. The decay, heat, removal, and so on. The accident lasted for a long time, but you could see here that the pressure inside the containment increased from 4.4 megapascal to about 0.75 megapascal. That suggests basically a hydrogen explosion, like what happened earlier on. And these are the valves, 8 safety valves in the primary containment. All of them failed to operate to vent the hydrogen from the containment as designed. Why? The springs on those valves were not able to operate because the containment pressure was very high and the valves could not operate. So here they describe to us how they used the safety relief valves with battery operations. The operators knew how to do it, and they probably saved the system from getting the accident from getting even much worse. So in that case, they used basically compressed air venting valve. It failed to operate because of suspected loss of pressure in the compressed air lines. So the operators used a non-manually operated relief valve, and they were able to eventually vent the containment. In a boiling water reactor of that design, this is the boiling water reactor has been through many, many different designs, but they have different classes of venting valves. In the case of steam, in that case, it was also mixed with radioactivity because of the failure of the steam relief valves. And here is an engineer describing why is it that those steam relief valves did not work, because those springs here could not overcome the pressure in the containment. So here we have a containment now that contains steam and mixed with hydrogen. And at some point, that hydrogen, hydrogen in general is very reactive, so it exploded, and we had definitely 3 steam explosions shown on videos taken by some TV company on the plant itself. So here is unit number, the 6 units at the Daiichi plant. Reactor number 1, you could see that the top here was destroyed. Reactor 2, the top was not destroyed, interestingly enough. This is after the accident. Reactor 3 had a fire there and it was destroyed. Reactor unit 4 was not operating. They had the core out for maintenance because they are testing some mixed oxide of plutonium and uranium fuel. And the core was out of the core, but the steam lines came into the reactor number 4, and they caused the fire there too. Reactor 5 and reactor 6, as I suggested, were built on higher ground than the units 1, 2, 3, 4. They were not affected by the tsunami. And basically, but unfortunately, well, fortunately, maybe they were not also operating. Notice here that this is a turbine plant here, and this is a turbine plant here, totally unaffected in unit 5 and 6, which were built on high ground. I repeat that again, that was a good design. All those 4 units built on low ground that was flattened intentionally, that was a bad idea or a bad design if you want to really characterize it. This is a turbine hall, and you could see that here there was no damage to the turbine hall, but then of course with the fires and explosions, the turbine hall top was affected in that case on unit 1 to 4. So even though we had 6 units, only 4 units were affected. So these are the 4 units that were affected, 1, 2, 3, and 4. And these are the turbine halls, 1, 2, 3, and 4 before the accident. And then you see here after the accident, unit number 1 lost part of its ceiling. Number 2, not much affected, in fact, by the accident. But number 3 had a bad fire. All the top there is gone. And number 4, that was not operating, was also somehow damaged. And you could see that the breeze have affected the top of the turbine plants, and they had only 2 stacks. Number 4 apparently caught fire because of the redirection of the flow of the hydrogen, the containment with the steam from one unit, this unit, to the other unit, so it caused the fire there. This is a bad design from the perspective of fault tree analysis. Each unit should be independent of the others in the case of accidents. This shows us here that the units also, the fuel in that case, because there is nothing other than the fuel, caught fire. And that means that the fuel that was stored in the fuel storage ponds, in a way, there wasn't enough cooling, and that fuel may have caught fire. This is definitely a fire here. Unit 1 is on the far left. The top only exploded, exposing the top of the reactor structure, the pressure vessel. Unit 2 did not, was not affected. And then you have a fire resulting from the hydrogen explosion, resulting from steam depressurization and fuel damage in unit number 3. And fire just starting on the side. Some people thought it was maybe tanks of diesel fuel for the diesel generators in the unit number 4. All right, so in that case, the plant now has a loss of power, and the loss of power meant that the decay heat is occurring, and they needed to cool the plant. And you could see here that they brought in helicopters from the Japanese Navy and the United States Navy. They had on Earth a large aircraft carrier by the area there. It was affected by the radiation, but they basically moved it away. Initially, they dropped water like in forest fires in the United States on top of the plant. That was not sufficient for unit, at least this is unit number 1. So they brought in fire engines, and they started pouring water into the reactor core where there was a fire, same as in the Windscale accident. Then they started bringing in lots of pumpers from the, of course, you find the firefighting people right here. The plant needed to use batteries to restore power to the control room and the safety equipment. So they asked the United States Navy to help. So they provided them with batteries that were only 2 volts in power for some reason. That was total failure. The people operating the plant were very inventive, very smart. So they went to their own cars. Imagine that, remove the 12-volt batteries and use them to eventually get some control on the instrumentation of the plant. And when we call it the station blackout, that was true. You could see here, This is the control room, totally blacked out. No power until they found car batteries to restore power to some of the instrumentation. Notice the earthquake here had destroyed the ceiling, and that is on March 26th. So that accident now in that case lasted about 11 days, a long time. I talk here about the previous earthquake events. As I suggested, reactors in Japan are very well built to withstand earthquake. So you find here that an earlier earthquake at another plant moved the ground under an oil storage tank. Oil is used in that case to drive diesel generator for safety equipment. Other earthquakes can also affect the piping. You would see here the ground has changed in such a way that the pipes connections were broken. So there is experience, and the plant was well designed for withstanding earthquakes, but not the flooding by the tsunami, unfortunately. These are the 4 BWR. Actually, no, that's at another site, I think. The reactors are cooled with ocean water and are about 148 miles northeast of Tokyo. So it's almost a distance between us here and the city of Chicago. And luckily, as I suggested earlier, the radioactivity found its way to the open ocean. This is a design of the advanced boiling water reactor that is built by General Electric in Fukushima. And this is the ground level or the grade level of the plant. You could see here these units. If you look at the legend, that's 32 here, 32 is a switch yard. So these are transformers. In the description of the accident, some people made a mistake, and they called that the diesel generators for the emergency core cooling system. That is not true. The emergency generator for the decay heat removal system are situated right here at 18. If you look at 18 here, you find here, oh, definitely the diesel generator. So how come they couldn't use those emergency core cooling system to cool the plant? Because here at the bottom, now look here, definitely below grade level, you find this unit here, 17. 17 is the ROC, reactor cooling stream, turbine, and pump. And that's the one that I showed you that supposedly would get steam from the condensate and quench it in the condensate or water from the condensate storage tank. So in that case, the safety equipment, the RCCs or the diesel generator were up. These ran out of fuel, but the turbines that are supposed to cool the core were all flooded and underground. In that case, they were not accessible to people running the plant. And this is in an advanced design of the boiling water reactor by Fukushima, but by General Electric and Toshiba. And definitely they'll have to redesign their system so that this safety equipment cannot be flooded in case it is close to a water source. This is a transformer that was affected by an earlier 1979 earthquake. So there is experience in Japan with these types of events that occur as a result of earthquakes, but not of tsunamis. So in that case, we are reaching the end of our lecture today. We are going to describe the type of accident that we call the station blackout accident. Along this line, I'm going to ask you to read an article before we cover the rest of the material in the next lecture. And the article, let's go there, is published in an environmental kind of a magazine, and simply write maybe a one-page, some kind of a summary for it. And let me see, I think I'll give it to you in the, assignments page. And our knowledge about the Fukushima accident should influence our future designs of boiling water reactors. I'll emphasize two aspects that should be looked upon more carefully, and they haven't been yet. One is a possibility of a steam explosion occurring, and it hasn't been really acknowledged yet. And the other one, what is the effect of the core spray system in generating the hydrogen in not just the Fukushima accident, but in existing boiling water reactors. And I'll stop at this for today and wish you a nice afternoon.